Hello, I'm Frederick. This is a joint work with Noam, Dor, and Elchanan, and it's about influences in mixing measures, okay? And we'll see precisely what that means if you've never heard of influences or mixing before. Um, but first, let's see where this whole area kind of started, which is like a very concrete question about elections, or so-called collective coin flipping, by Ben Orr and Linnell. And so here's a question about electoral systems, like the way we say elect a president in a country. And so what we're going to consider more precisely is that there's going to be n voters, and each one of them has an individual opinion, and there needs to be some kind of mechanism, which we'll call F, which aggregates everyone's individual opinions and decides, say, who actually gets to be the president. Since probably everyone is not going to just spontaneously agree on who should be president. Okay, and what we're going to consider, and what Ben Orr and Linnell proposed, is that everyone is deciding their opinion kind of just by flipping coins. So it's not that we think this is real, like we don't think that that's exactly what's happening in real life, but this turns out to be an interesting model to study. And so we're going to start there and then revisit this assumption later. And the nice thing about having a model is that you can start to study questions about the model. And so in particular, we could try to figure out what's kind of the best voting system, or which systems are worse than other systems. And one kind of question you can study would be some notion of manipulability, or the ability of an election to be controlled by a small coalition of voters. And so what does it mean that the election can be controlled by a small coalition of voters? Basically that there would exist a small set of people, and if they all decide to vote for candidate one, then it's very, very likely candidate one wins. And if they all decide to vote for candidate two, then it's very likely that candidate two wins, something like that. Now we can only really answer these questions once we have a probabilistic model. You can imagine the answers might depend on the model, but for now, let's just accept this model. And so now let's make this a little bit more precise. Okay, so first of all, this is not strictly required, but let's suppose that the voting system is kind of reasonable, so it's monotone. So if someone flips their vote from minus to plus, and plus is the winner, then plus stays the winner, and likewise for minus, okay? So it's just saying that there's no incentive for someone to vote for the opposite candidate of the one that they want to win, okay? So any reasonable voting system will probably satisfy that. And now, the mathematical question we want to answer is, how large does M need to be such that there exists a set of voters such that if they all decide to vote for one, then candidate one wins with probability 99%. Or there exists a set of voters such that candidate minus one wins with at least 99% probability. Okay? Now, again, realistically, maybe most voting systems are kind of symmetrical in the candidates. So we could have additionally assumed that the voting system is symmetrical, and then it doesn't really matter if you're thinking about forcing the election for plus or minus. But yeah, I guess it's not strictly true that all voting systems are symmetrical. And anyway, our results will be more powerful because we can consider asymmetrical ones. You might wonder if there might be some weird way that non-monotone functions could be better than monotone ones. But actually in the original paper, there was a clever argument to prove that monotone functions are kind of the most resilient to manipulation. So we'll just consider monotone functions for the most part in this question. And now let's think about some examples. So how many people do you need to control so that you can control the election with 99% probability? Well, one of the most common electoral systems would be a majority vote. Okay, so everyone votes, and then we see who has more votes. Seems like a pretty reasonable system. Now we can analyze this using the central limit theorem because we assume the voters are independent. The the sample mean is going to be Gaussian, and then if we rescale it by 1/squared n, it's a standard Gaussian, right? And we're generally speaking, going to think about the case where n is large. And so for the majority vote system, it suffices to control a subset of squared n many voters. Okay? And of course, that's not the only electoral system. So another electoral system would be a dictator. Okay? So for example, I could decide that person 1 is like the king and whatever they decide goes. Okay, so that's a very simple to implement electoral system. In this case, most people, if you control them, it doesn't really matter. But if you control the single dictator, then you can change the decision, right? So at least from the perspective of not being controlled by a small coalition, it's clear majority is better than dictator. But you might wonder, well, are there things that are better than majority, for example? And these are the kinds of questions we can study mathematically. Now, let's make some additional definitions. So this question kind of doesn't make sense if, like, for example, f is always equal to 1. There's kind of nothing to study. So for now, let's say that electoral rule is almost balanced if the probability of f equaling 1 is around 1/2. It's not really crucial that it's exactly 1/2. On the other hand, again, it's generally speaking a desirable property of the electoral system. And now we could say, well, we want to design the best voting system, so we'll say, okay, well, given the constraint that it's almost balanced and monotone, we want to make M as large as possible. So a small coalition of voters cannot control the election. And an interesting line of work that studied this question led to the discovery that there exists a monotone, almost balanced function which can handle a coalition of size up to around n divided by log squared n. Okay, so that's much better than majority. And in fact, it was also shown by Kahn, and Lineal that every almost balanced function can be controlled by a coalition of n over log n voters. So there's only a gap of log n between those two results, so we are close to knowing the optimal answer to this question. It should be said that these electoral systems, they're not quite what we use in everyday life, but yeah, they do have these interesting properties that they're close to the optimal resilience level. And that can have some applications in other areas like complexity theory. Now, Kahn, and Lineal, they proved this result. But one thing that made their work, I think, very exciting was that they obtained as a corollary of this interesting isoparametric theorem. Okay? And so here's the theorem. So there's the inequality. Ignore the figure on the right-hand side just for the moment. So what KKL said is that for every function, from plus minus 1 to the n to plus minus 1, the variance times log n over n is a lower bound on the maximum influence. Okay? And what's the influence? The influence of voter I is like the probability that they can flip the election, right? So this is written precisely here, but if it's like, the probability that their vote changing from plus to minus is pivotal for the election. So you can imagine that's not going to be, in most systems, extremely large, unless it's like a dictator system. But the real question is how small is the influence? And so in particular, the KKL theorem tells us that if the election is almost balanced, so the variance is around 1/2 or 1, depending on how you normalize, some voter always has at least log n over n influence, okay? And if you try to directly prove this from the definition, it's not trivial. With not too much effort, I think you can prove that some voter has omega 1 over n influence. But yeah, it turns out that's not the optimal answer. It's kind of like a very interesting and I would say probably unintuitive fact that someone has to have log n over n influence. Like we saw it's true for majority, and we saw it's true for dictator. But you can imagine other voting systems would be more resilient than those. In fact, there is a voting system called tribes, which plays an important role in all of these nearly optimal constructions. And this one actually achieves the bound on the influence. So the way the tribes works is that for candidate 1 to win, there's going to be these tribes which each have R people, and at least one of those tribes has to unanimously decide that candidate plus should win. Okay, so that's the tribe's function, and if you set the number of people in a tribe correctly, then it turns out to achieve this bound. Okay, so this inequality is actually sharp up to constants. And well, you can kind of imagine that if at least one voter has log n over n influence, then you could do some kind of iterative argument to show that there is a coalition of size n over log n which controls the election. Yeah, and this can be done without much effort for monotone functions. Okay. Now here's an interesting side note, or I guess connecting back to the real world. We can ask, well, are voters identically distributed? Are they independent? Okay, and so these are just some plots. So these are plots I found which show the outputs of some real elections. Okay, and this is like in New York City. I mean, one thing is it's kind of very clear that the voters are not just flipping coins, because this diagram does not look very homogeneous, right? Like people in one location are much more likely to vote for one candidate than people in another location. This is another election, like presidential election. Again, you can see that things seem to be very spatially correlated. Yeah, and I guess it's really, if you think about it, it's like not super obvious just by literally looking at the pictures that the voters couldn't be independent. Like maybe they're biased in some way, but they're actually independent. But of course, like if you look more into like election forecasting and stuff, like it seems pretty clear that unless if you're omniscient, then maybe the election is deterministic. But from like a practical perspective, it seems that electors are very correlated, say between states which have similar properties. If they're close, then it's more likely than if they were independent that they're going to both swing the same way, for example, right? So elections seem to be not ID in real life, and I think that's not controversial. Of course, in social science, people have studied, how do people's interactions affect them. Okay. And so, yeah, one other thing you might wonder is like, well, is the conclusion of KKL reasonable in real life? As far as I know, in most elections which are close, okay, so KKL only really says something for a close election, right? Because the variance needs to be large. It doesn't literally apply in real life, but you can look, okay, in elections which happen in real life, how thin of a margin are they by when they are at least forecasted to be close beforehand. And okay, these are just some numbers I collected, from, like, you can look at the 2020 election. Actually, you would only, at least after the fact, you can realize, okay, there's a few states that were very, very close. So if you just flipped a few voters in those states, then it would have changed the output of the election. And famously in 2000, it was like way, way fewer people. It was like 537 people. If they had voted differently in Florida, then a different winner would have been picked. This is a little bit incomparable to KKL because we're like looking at the output of the election and then picking the voters. But I guess generally speaking, if you were to control voters in so-called battleground states, then a fairly small coalition does seem to control tight elections. Okay, and yeah, you can compute n over log n. It's much bigger than the threshold for these elections. Okay, so it seems that, yeah, actually, if anything, KKL is kind of a little bit, conservative. Actually, in close elections, it seems that very small sets of people, at least in the examples I've seen in US politics, do control the election. Okay, so it seems reasonable that KKL may not really be a phenomena which is limited to this toy model of independent IID uniform voters. Okay. Now, here's a question. If we think this phenomena is more general and not really like a fluke of this independent voter model, well, how can we study that mathematically? So how can we write down a mathematical model? And in what kind of models would KKL be true, and in what kind of models would KKL be false? And we're not really the first people to try to think about this. So there were a bunch of interesting works about generalizing KKL beyond its original setting. These are a few of those works. But we'll talk about there's lots of choices for models. They were studying things that are probably more natural from graph theory perspective, like connections to Cayley graphs. And let me tell you about a different kind of model, which maybe is a bit more motivated by, the kind of models you would use to model people, say, in a social network. And these are models on graphs. So in social science, there's a long history of people constructing graphs to try to understand the relationships between people. So you can read about Jacob Moreno. He was one of the first people to do this. He came up with this graph which represents some of the social dynamics in an 8th grade class. Okay, and I think everyone probably agrees social relationships, which more or less could be visualized with a graph. They are very important in how people decide things. There are some very interesting experiments, which I just put a reference here, where people actually did some kind of randomized control trial on Facebook. And they were able to show some effect that, what people's friends are posting really does seem to affect them. So I encourage you to look into that if you're interested, because I saw this is a very interesting result. Okay, but the summary, it seems that at least some part of the correlation between people is probably caused by interactions that can be modeled on graphs. Their friendship network, their spatial networks. And then one kind of standard tool we use to model this is a so-called Markov random field. So this is a distribution over X whose log likelihood is the sum over cliques of a graph of clique potentials Fk of X. Okay? And so we're going to consider models like this in this work, and that's by far one of the most common ways we model these kinds of correlations. They're very natural from a variety of perspectives. And those kinds of models were very successful in understanding phenomena of statistical physics. So let's just briefly summarize what happens for the 2D Ising model. That's one of the most famous stat-mech models. It has a phase transition. At low temperature, you have this spontaneous symmetry breaking. So in the first picture, almost everyone agreed to vote for, in this case, it's black and white. So almost everyone is voting for black color. And the interactions are on a graph. That is the 2D grid graph. And think about it for a moment. KKL is actually not really going to be true if everyone just spontaneously agrees together that they're going to vote for the same candidate. So if you look at the majority function, it's extremely far, even if before everyone spontaneously agrees. So imagine basically the model is everyone is going to be equal plus with 1/2, or everyone equal minus with 1/2. So you think about a majority vote, you would need to control a huge number of people to change the outcome of the election in this case, because the election is won by omega n margin. You can actually compute the exact large deviation probability using results from probability theory, but it's extremely small. So influence is very tiny. On the other hand, in high temperature, people are not super correlated. It's very different from ID measure, but still, there's no, for majority of votes, it seems very reasonable, for example, that KKL is going to be true. And we can ask if for general election rules it's going to be true. And one way you can understand the high temperature phase is that you have rapid mixing of the Glauber dynamics. So it's a dynamics where you pick a person uniformly at random and have them resample their vote. And then you ask how long do you need to run this to forget your initialization or get to the stationary distribution. And we know that this is a dynamical way to characterize the high temperature phase of the model. And there was a lot of beautiful work on this, and it was proved in the 90s. Okay? And so we've realized, actually that's pretty much seemed to be the key thing that's going on, what I told you in the previous slide. So the KKL is true. Now I'm going to not assume everyone's independent, but I'm going to have a general Markov random field model. And I just need 3 assumptions. One is this high temperature condition that the Glauber dynamics are rapidly mixing. We kind of discussed in the last slide, for the low temperature phase of the Ising model, KKL is not going to be true. So this assumption is clearly quite important. Second thing is that we have a Markov random field. We're going to assume the graph is bounded degree. It's kind of an interesting technical question to see if you can relax that, but for example, the number of friends with a person is much smaller than the number of people in the world, so it's kind of a common assumption. And the last thing, another assumption is that even if you kind of condition on everyone else's votes, you are not absolutely certain about one person's vote. So this is, again, like a very common assumption. I think is pretty reasonable in this setting. Okay, so the point is, it turned out actually for a huge class of models, KKL theorem is true just like before. Okay, so with the remaining time, I'm going to say a little bit about the proof idea. This part might not make so much sense if you've never thought about these things, but I'll try anyway, and if you read the paper, I think it will make sense. So the idea is we're going to look at the behavior of the dynamics, okay? And so we can look at what's called the heat semigroup, which is we run the dynamics for around nt steps and look at the expectation of the function of the final state conditioned on its initial state. And it turns out the variance of a function can be written as the difference between the L2 norm at time 0 and the L2 norm at time infinity. So you can use the fundamental theorem of calculus to write the variance as an integral over the heat semigroup. This was used by Bakri, Emery, and others. So this is a very classical trick in this area, or at least in the area of Markov chains. And what happens is you get a bunch of operators. The operators commute. So Cordero, Raskin, and Ledoux realized that you can do this trick where you calculate out what the derivative is. I wrote the formulas there. You basically get a partial derivative, Li, and it actually, in the independent case, commutes with the heat semigroup. So you flip the order, and then this is like really, really good because once you have the heat semigroup on the outside, there's this really important inequality called hypercontractivity, which is basically equivalent in the setting I'm talking to rapid mixing of the dynamics. In particular, is equivalent to log Sobolev inequality. And as soon as you get the HT on the outside, you just know you can apply hypercontractivity. It can basically it can bound the norm of the function after applying the heat semigroup by a different norm at the initial time. Okay, and more or less all the proofs of KKL use some idea related to hypercontractivity, but this is like a very clean way to do it, which was due to Cordero, Raskin, and Ledoux. And actually, once you do this, it's kind of just a relatively straightforward calculation with calculus to get the following inequality, which is called Talleyrand's inequality, which is a general isoperimetric inequality that holds for all functions f, and in particular can be shown to imply KKL. Okay, and so this was kind of where we were before this work. Is that there were many proofs actually of KKL. So Talleyrand also had a different way to prove his inequality. But this, was one of them, and it works really great for independent measures, but it doesn't work so great for for dependent voters because the HT and the LIs, they don't commute. Okay, and like the meaning of this is like if you update at site I and then run the dynamics, then once I changed my vote, like everyone starts to see, oh, I changed my vote, and then the way that they change their votes, affects their neighbors and so on. And so that's fundamentally why these two operators don't commute, okay? And so it seems that HT-LI and LI-HT are very different, and this is closely related to why KKL is not true, say, in the low temperature case. I mean, this non-commutation is like how it manifests. And like the really nice thing is that, okay, there's a story about why these things don't commute, but you can actually be very serious about this, and you can actually write down a explicit formula which tells you how much they don't commute in terms of so-called commutators. This is a fact which is known in like representation theory and quantum mechanics, can be proved directly. So you get an expansion for how these operators don't commute, and in short, it gives you a bunch of terms which correspond to different subgraphs. You can control this subgraph by subgraph, and that you can bound the effect of the non-commutation. It actually only works for small t, but you can actually show this suffices because when the dynamics mix rapidly, what's happening at small t is kind of all that really matters in some sense. So that's a very high-level summary. Please read the proof if you want to understand it. The proof is actually relatively short. And so, like it's not like a crazy complicated proof, but now we've been able to show that KKL is holding in quite a much more general situation. Okay, there are a lot of open questions. I think I'm kind of a little over time even for the recording, so I'll just flash these here. There's a lot of interesting questions, and thanks for listening.